Hello everyone, this is Professor Keen. I'm lecturing once again on Newton's laws of motion, which are recorded in chapter 21 of A Student's Guide to the Great Physics text. This is from Newton's Principia. You might recall in my last couple of lectures, I mentioned Newton's first law, which basically says what happens when there are no forces acting on a body, or more specifically, when there are no unbalanced forces acting on a body. That is, it continues in its state, whether it's a state of rest or a state of uniform motion. The second law, on the other hand, says what happens when there is an unbalanced force acting on a body. That is, its momentum changes, and the momentum change is in the direction in which the net force is applied. So I think in last lecture, what I did is I gave an example of how to use Newton's second law of motion. I want to develop this thought a little bit more, so we'll talk about Newton's second law of motion. I'll probably finish this law and then talk a little bit about Newton's third law. Okay, so the way that we had been writing Newton's second law is like this. The change in momentum of an object is equal to the unbalanced force that is applied to it times the time interval during which this force is applied. We can rearrange this, and so what I'm going to do is I'm going to divide both sides by delta t. So if we divide both sides by delta t, you see they cross out over here, and then I'm going to just swap sides. So write this as force equals delta p over delta t. You can think of this as the net force on the body. And this side here then, we can think of as the rate of change of momentum. So the bigger the force, the more rapidly the momentum changes. So it's a change in momentum during a time interval. So force is delta p over delta t. For those of you who are somewhat familiar with calculus, and even for those of you who are not, there's something you can do. You can say what happens in the limit as delta t approaches 0 of this quantity delta p over delta t. So as you get smaller and smaller time intervals, this goes over to what we call a derivative. So this is the notation that Leibniz introduced for describing derivatives. So that as you consider smaller and smaller time intervals, the limit as delta t approaches 0, we write this as a derivative dp dt. And in that case, we can say that the force acting on an object gives you the rate of change of momentum dp dt. So sometimes you will see Newton's second law written in this form. We can also think about it as written in this form, and then also this form up here before I canceled out the delta t's. Now, so this is the form you'll often see Newton's second law written in. But for those of you who might have taken some physics before this class, you might have seen Newton's second law written as force equals mass times acceleration. So the question is, what is the relationship between this form that we've been talking about up until now and this form you perhaps learned in high school, F equals ma? So I want to say a few things about that. So let's start with how we are thinking about it. Force is dp dt. And now let's realize that the momentum, this quantity right here, momentum, remember was defined as the object's mass times its velocity. So if I write d by dt of mass times velocity, that's the same thing as this equation right here. Okay? Now those of you who've taken calculus will probably remember when you have a product like this, you can use the product rule and write this as dm dt times velocity plus mass times dv dt. Okay, so this is taking the derivative of the first term times the second plus the first term times the derivative of the second. Okay, so this is dp dt expanded like this. And now what we can do is we can realize in most situations, the mass of the object is not time dependent. So dm dt, in many cases, that goes to 0. And then we have mass times dv dt. And you probably, some of you will recognize, well, this term of course goes away because 0 times anything is 0. This term right here, dv dt, we can write this as the acceleration. So we see right away, we get F equals ma. But it's important to keep in mind that this formula is a special case of this more general formula. And this special case only works when the mass is not a function of time. That is when dm dt equals 0. There's no mass change. Then you can use this. In some situations, the mass of an object is changing with respect to time. So for example, if you have a rocket, let's say, and its mass is the mass of the metal plus the mass of the fuel inside of it, and as it's flying, the mass is burning, the rocket fuel is burning, and so the mass is decreasing over time. And so this formula becomes more difficult to use in situations like that because the mass, in fact, is changing with respect to time. So in many cases, this formula will actually be the more useful formula. I should say another thing is that this formula right here is consistent with Einstein's later theory of relativity, whereas this one right here is not. So this is the better, more general form. right here. But this formula works in many cases, but not all cases. So I should probably just lay that out at this point. Okay, should we do another example of how to do this? Tell you what, here's what I'm going to do. I'm going to now go on and introduce you to Newton's third law of motion, and then I'll probably do one more lecture on Newton's third law of motion and explain a little bit more about it. So let's just talk about Newton's third law briefly, and then I'll probably run out of time. Newton's third law of motion. How did Newton write his third law of motion? I'll just write it the way he did. Well, actually, he wrote it in Latin, but I'll write an English translation of it. So to every action, there is always opposed an equal reaction, or the mutual actions of two bodies upon each other are always equal and directed to contrary parts. So let's parse this. What does he mean by this? It looks kind of lengthy. The short version of this is, for every action, there's an equal and opposite reaction. That's a quick way to say it. But I always say that this law is the easiest to say, but actually the most complicated and most misunderstood of the laws. Okay, so let's kind of go through and make sure we understand what he's talking about here. So to every action, let me get rid of these right here. To every action, there's always opposed an equal reaction. So you keep in mind, first of all, that action and reaction, these terms, action and reaction, are synonymous with our terms force, or and counterforce, you might say. So to every force, there's opposed an equal and opposite force. Okay, so that's something to keep in mind, first of all. Or the mutual actions of two bodies upon each other are always equal and directed to contrary parts. So I think it kind of makes sense. These forces are equal. That's what this is saying. They're equal in size, directed to contrary parts. This is just a way of saying that they're pointed in opposite directions. I suppose this language maybe is used in, I don't know, in the American South still, perhaps Texas. Are you from these here parts? It's sort of this direction or over here. So the forces are directed to contrary parts, that is in opposite directions. So what's the kind of example that Newton uses to describe this law? Well, he says, for example, if your finger pushes a stone, then the stone pushes back on your finger. So let me make a little drawing here. Okay, so we've got okay. All right, well, this is okay. It's not a great drawing, but oops. All right, so here is, I guess this is your finger, right? So draw a couple. It's your knuckles. Okay, so there's your hand. And here's a stone. Okay. So here's your stone, whatever. Okay, and what this is saying is if your finger is pushing on the stone is pushing back on your finger. So if I were to draw a free body diagram, as I mentioned before, represent your finger by a dot, there's the stone pushing on your finger, force of the stone on your finger, and then draw another free body diagram. This represents the stone, and this is the force of your finger acting on the stone. So it's important to keep in mind that these two forces are not acting on the same object. So we have two separate free body diagrams. On the one hand, you have a free body diagram for the stone, and you have the finger force pushing on the stone. And on the other hand, you have this free body diagram representing your finger and the stone pushing on your finger. These two forces right here are the equal and opposite forces that Newton is talking about in his third law. They're equal in size, and they're directed to contrary parts. They're directed in opposite directions. So that's an example of an application of Newton's third law. Okay, so tell you what, why don't I stop there, and with next time I will do another example problem to help clarify this.